All right, welcome everyone to my 11.5 in-class video. So this is taking the, or replacing the 11.5 material that I would have covered in class. As far as administrative announcements goes, there could potentially be a lot of administrative announcements regarding a whole variety of topics related to MSU canceling and all that sort of stuff. I just want to emphasize that you check D2L, and we're going to post our announcements on there. And that's kind of where we're going to be combining kind of all of our classes and have a united front here in Math 133 as far as keeping everyone up to date with things. So I am not going to do any administrative announcements here. I'm going to just defer to D2L, and we're going to post things there instead. So that's how I would normally start my class. Next on, I would move to talking about the video notes that you should have watched before coming to class. So it's a little bit funny having a video explaining the video notes that theoretically you could have just watched. So this is assuming that you've watched kind of the original course videos for 11.5. If you haven't watched those, I definitely would recommend that you pause this video here, go and watch those, and then come back, because you're going to get a lot more out of this video having that knowledge under your belt. So, but I would like to do a quick recap, the things that I think you should have really taken away from those videos, and then we're going to get into the new problems for this video. All right, so first of all, in this section here, we formalize something that came up back in geometric series and even when we had sequences and whatnot, this notion of having an alternating series. So alternating series, these are the things that go kind of back and forth, positive, negative, and we found a great way to make alternating series or alternating sequences even is having this -1 raised to some power. So when you have this -1 raised to some power, and that power is, right, you can have this either raised to the nth power like we have here, or n-1, or n+1, or n+2, or anything so that it's actually alternating between the positives and the negatives. That's going to be a fine way to represent an alternating series. So that's what we mean by alternating series. Here's kind of a classic one up here, just a bit of an example. And quite often for these alternating series, it's very useful to separate them, right? So you kind of have the alternating piece, and then you can talk about this other piece, which should be just strictly positive. So that's what we call by these b sub n's here. It's a little bit annoying, right, that they're double using notation, right? We already had a sub n's and b sub n's and all that sort of stuff when we talked about like the limit comparison test and things like that. So you have to be careful exactly what are you talking about. These b sub n's are just the positive pieces of some alternating series, some overall a sub n thing here. So, okay, and likewise, you could have this where, again, you kind of strip off the alternating piece and then you just have the positive piece. So that's the big thing. That's what we mean by alternating series. And in that case, we have this thing, the alternating series test, and that's the main thing that we're trying to learn how to utilize in today's class. So here it is. Again, kind of it talks about you need to kind of take off this alternating piece and just have the positive pieces. So we're going to isolate just that bit there. I usually have students ask me, does it matter that this one has raised to the n-1 power? Can it be raised to the n power? And the answer is absolutely. And likewise, this n=1 as your starting point does not matter at all. You could have n=2 or n=3. So those are some upgrades that, even though this is how it's written in the book and how we have it in the video notes, those aren't important at all. So you can, again, change that to n=15 if you'd like. And you could have it raised to the nth power and all that sort of stuff. So any of that is fine. So the big thing, we need to isolate these b sub n's, the piece that's positive. So you forget about the alternating piece. And here's what the alternating series test says. It says if you have a decreasing sequence, that is when you plug in bigger things, you go farther along your list, they should be getting smaller and smaller and smaller. But again, they should be positive, right? It should stay greater than 0 here. That's the first thing that you need. And then the second thing that you need is that the limit of these positive pieces needs to go to 0. And if these two hypotheses are met, then we can actually conclude that the series converges. All right, so that is the big thing for these video notes. And then, of course, we do lots of examples with those. But I'm not going to go through those because, again, you probably just watched those videos. And so that's really all I have to say as far as a recap goes. So then, why don't we go ahead and we're going to get into our new stuff for today. So this is week 10, and again, here are my new problems that I'd like to talk about in this video. So starting off, right, with example number 6 here, apply the alternating series test to the following to determine if they converge. If the alternating series test cannot be applied, explain why. So here's my first one, and okay, so we know that there are some conditions in order for the alternating series test to work, right? It doesn't work for any old series. We see that, right, there is an alternating piece, that's great, and so we probably want to go ahead and remove this alternating piece, or just focus on these b sub n's, right, the solely positive piece. So let me go ahead and write, I'm going to say equals to, and I'm just going to do a quick rewrite here to just isolate these positive pieces, right? So this is going to be 1 over 2n plus 5. All right, so that right there, these are our b sub n's. And now remember, we need two things. First of all, we need that the b sub n's are decreasing and positive, of course. And then second off, we need that their limit should go to 0. So the limit as n goes to infinity of the b sub n's should be equal to 0. That's what we're hoping for in order to show that the alternating series test would conclude that this converges. So, okay, we need to check, are the b sub n's decreasing? Well, yes, they are, right? And this kind of goes back to a lot of what we were talking about in 11.3 when we were doing the integral test and whatnot. We have that 2n plus 5 is an increasing function, right? If you were to draw this on maybe a graph or something over here, right, 2n plus 5 would look like a straight line. You would have raised it up by 5, all that sort of stuff. But yeah, this is increasing, right? As you plug in bigger and bigger n values, it gets bigger and bigger. Okay, so 2n plus 5 is increasing, so we know the reciprocal of an increasing function is decreasing. So that's all my work that I would need to show for giving us that this is decreasing, so that's great. And the next thing we want to check about this limit as n goes to infinity, right? We hope that it's equal to 0. Let me go ahead and erase this really quick. So I'm going to say the limit, and again, you only use this positive piece, this 1 over 2n plus 5 here. So you only isolate that positive piece. And well, as n goes to infinity, right, 1 is just constant, so you're going to have 1 divided by a very, very large number here. This is indeed going to be going to 0. There's just not a lot of work to show here. I suppose that you could, you know, for a little shorthand, you could do just 1 over infinity. That's not really proper math so much, but you could go ahead and write this just so you kind of realize what's going on here. And again, this is getting larger and larger in your denominator, and so it goes to 0 overall. So yes, these two things are indeed met, and so we can say, so by the alternating series test, that our series here, summing up from 1 to infinity, negative 1 to the n of 1 over 2n plus 5, that this converges. You should also notice, right, that the alternating series test will only conclude that something converges. It doesn't have the power to conclude that something diverges, at least not how it's written here. And so if the alternating series test doesn't work, we need to use some other test to show that it diverges. But luckily, in this case, we have that it converges. So there would be my final answer, and I would probably really emphasize, right, it's why does it converge, right? It's by the alternating series test. And it's fine if you want to abbreviate that, AST. We all know what that means. Okay, so let's move on here to our second problem. Again, oops, went too far. Again, I see that I have this alternating piece. That's wonderful. It gives me hope for the alternating series test. But now let's go ahead and look at these b sub n's. And again, we need to make sure that they satisfy those two conditions. So at this point, I would like you to go ahead and pause the video, try this one on your own, see how far you get, and then we're going to bring it back together and go over the answer together. So again, please pause the video, work on it now. All right, so here are my results. You can see that actually neither of these things work out, for this particular series, right? We needed that it was decreasing, and we need that the limit of just those positive pieces, this tangent inverse of n, should go to 0. And sadly, it doesn't satisfy either of these, right? And remember, we need it to satisfy both. So I've really gone above and beyond here. Really, you would only need to show that one of these two things fail. But actually, in this case, both of them happen to fail. So really, you just show one of these two, right? If this was like a quiz or an exam problem or something like that, you could just say it's not decreasing. And that's enough. As soon as one of the things fail, the alternating series test does not apply. So, okay, well, it does not apply. And so we can't really use it here, but still, what if we had this question and we were, we had to decide, does it converge or diverge? What would we do next, right? So imagine we got this on a quiz or an exam and we had to kind of justify, just does it converge or diverge? We had this thought, maybe we can use the alternating series test. It turns out we can't, so what do we do now? And my claim is, right, when the alternating series test does not work, it does not apply, but you have an alternating series, a great step to take next is to use the nth term test for divergence. So I'm going to go ahead and I'm going to consider the nth term test. So remember, the nth term test for divergence says that if your limit of your a sub n's, so this is the overall series here, is not equal to 0, then the series will diverge. Then the series of the a sub n's diverges. And so my claim is that we can apply this to this problem here and darn near every other one where the alternating series test does not apply to an alternating series. And so it does require a little bit of a sophisticated argument here to figure out what this limit of the a sub n's are. Because remember, when I graphed this up here, so this was my picture of tangent inverse, right? It didn't include this alternating piece. And so if I was to include this alternating piece, remember, well, they're going back and forth, positive and negative, so on and so forth. So for instance here, for when I was to plug in n equals 1, right, this would actually be a negative value, right, because I'd have negative 1 up here to the first power, so that would be negative. But I have it marked down here as positive, right, because I was just graphing the positive piece. So in reality, this should be a negative answer. And then it goes, and it's positive, right? When I plug in n equals 2, that negative 1 squared, that's going to be positive 1. And then when I plug in n equals 3, that's going to be back to being negative. And then n equals 4, that's going to be positive. And n equals 5, that's going to be negative. And it's going to jump back and forth here. And so my actual series kind of looks like these blue dots here, where it starts off negative, then positive, then negative, then positive, then negative, and it goes back and forth forever. And so I'd like to point out here, right, if you were to look at, oops, erased too much. If you were to look at just the even ends, right, so for n, or I'll say for even n, that the series gets close to pi over 2. So, oh, sorry, not the series. The sequence gets close to pi over 2, right? So for even n, the sequence gets close, I'll just say gets close to pi over 2. And for odd n, the sequence gets close to negative pi over 2, right? If you were to just follow all of these odd ones down here, they get close to negative pi over 2. Down here, the other asymptote for tangent inverse. And if you just follow the even ones, right, they're going to get close to positive pi over 2. So remember, for a limit is one real number, right? You can't have a list of real numbers or things like this, right? If it doesn't go to one particular thing, then we say that the limit does not exist. So in this case, the limit of our a sub n's, well, half the time it's getting close to pi over 2, half the time it's getting close to negative pi over 2. It's oscillating back and forth, back and forth, back and forth. And so in this case, our limit does not exist, right? So our limit overall, it can't decide what it's going to go to. It kind of just switches back and forth. So this overall does not exist. And remember, we're looking for anything that's not 0. So it does not exist, well, that's certainly not 0. So therefore, it will diverge by this nth term test for divergence. So our series summing up this negative 1 to the n of tangent inverse of n diverges by the nth term test. All right, there we go. All right, let's see. Well, I would say any questions here, but I guess if you have any questions, right, this is a great time to remind you guys about Piazza and whatnot. I would be tempted to say you could just post questions, in the comments section here for this YouTube video, but we're going to probably embed this in D2L, and plus we can't really respond so well with LaTeX, in math mode and stuff like this. It's just a regular text box there. So I would recommend, if you have any questions, post them in Piazza, and we'll definitely be checking that a lot now. Okay, moving on. Again, we're playing the same sort of game. Apply the alternating series test to the following to determine if they converge. If the alternating series test cannot be applied, we're going to explain why. All right, so with this one, let's go ahead and check, right? Again, we need to check that it's decreasing. So that's the first question. And we need to check this whole limit business. So limit goes to 0. So those are the two steps that we need to use every time we're considering the alternating series test. Those are the hypotheses. If those are met, we know right away that it converges. All right, so let's look at decreasing. Well, for decreasing, again, we need to isolate just the positive piece, right? You're not looking at the entire thing. You're just looking at solely the positive piece. And we're looking at, does this decrease? And, well, okay, this is fairly complicated, right? I know what sine looks like, for instance, but this whole pi over n business makes things more difficult. So let's maybe do a quick sketch here of what's going on. And something like this. And let me draw my sine function. I don't know how much I need, so I'll just draw a little bit of it here. Okay. And now let's pretend we were starting to plug in specific values, right? So we start off at n equals 1. So at n equals 1, if I was to plug that into, n, well, we'd have sine of pi over 1. So sine of pi over 1, that's going to be all the way out here. So this is when n equals 1. Sine would output 0. All right. So next up, if I was to plug in n equals 2, n equals 2, we'd have sine of pi over 2. Sine of pi over 2 is going to be 1. So this right here is when n is equal to 2. And already I can see we have a problem, right? This did not decrease. I started off here at height 0 when n equals 1, and then I ended up here at height 1 when n was equal to 2. And so the answer is no, it does not decrease. Does not decrease. And the problem here was kind of immediately the difference between n equals 1 and n equals 2. So with n equals 1, technically the alternating series test does not apply. But I want to show you something that actually, if we were very clever with this, we could get the alternating series test to still work for this. And so let me jump down here really quick and mention why maybe we should still have hope with this. And that is the limit does go to 0, right? So the limit as n goes to infinity of, again, we just look at the positive piece, so sine of pi over n. As n gets very, very large, right, this is going to be going to sine of 0, and sine of 0 is just 0. So that piece, it does actually work. So again, as this one sits, it does not apply. However, if we make this small modification, right, and this would be like a fun challenging problem sort of deal, right, if I just plugged in n equals 1, in this case, we get out 0. So this would be, right, again, if I did n equals 1, the series outputs 0. And then for n equals 2 and beyond, right, let's just say that this is, we need to sum up the values still, right? We need to sum up from n equals 2 all the way to infinity of these negative 1 to the n, sine of pi over, oh, that's a bad n. There we go. And now what actually happens, let's see if we continue this process down here, right? So now if I'm starting at 2, we don't have this problem point, right? N equals 1 was a problem point, and so we didn't like it, and it kind of ruined the alternating series test for us. However, right, starting at n equals 2, we're kind of at this peak, and if I did n equals 3, right, so that means we'd be plugging in pi over 3, so that'd be maybe somewhere over here, it starts to go down. So this would be, again, n equals 3. And at n equals 4, right, it goes down even farther. N equals 5, n equals 6, n equals 7, n equals 8, 9, right? We have pi divided by larger and larger things. It's getting closer and closer to 0 here. And so at each one of these, it does decrease from the one before it. And so starting at n equals 2, it actually works. And so we do get a decreasing function. So at n equals 2 and beyond, it is decreasing. And so usually when I show a problem like this, the question is, wow, I mean, it's clever, it's interesting, all that sort of stuff. Am I expected to be able to do something like that on a quiz or an exam? And the answer is, well, probably not, right? I would have to do an awful lot of leading and writing and stuff like this in order to get something like this to work on an exam and not just kill everyone. So again, this would be quite challenging, and so no, I think that it's a good in-class problem. It's wonderful for us to be able to talk about it and think about it together. But as far as a timed assessments goes, I think it's on kind of the very upper end of the spectrum. That'd be difficult to do. All right. Well, with that, we have another problem. So again, I invite you to please pause it here. Try this one on your own. I think this one is quite reasonable for a quiz or an exam like setting. So please pause your video, try this one out on your own, and then we'll resume it together and go over this one. All right, here is my work for my final answer. I'm realizing that this is not the most beautiful n in the world here. Sorry about that. But again, we need to kind of break it up and look at just the positive piece for the alternating series. So that's why I've rewritten it like this. We know that it's decreasing because this function right here is increasing, right? Certainly n to the 5th plus 3 is increasing, and the cube root is an increasing function, so compositions there, that's going to be increasing. And so the reciprocal is decreasing. So that's half of it. The other half is that we need to make sure that that limit goes to 0. And again, the numerator is just constant. It's regular old 1. And so as you plug larger and larger things in to the denominator and it's increasing, right, it'll eventually go to infinity in this case. It gets larger and larger and larger. And so 1 divided by a very large number is going to be 0. And so those are the two conditions for the alternating series test. We've shown that they both work out. And so by the alternating series test then, we know it converges. All right, with that, let's go ahead and move on. And I want to give you a little bit of bonus math here. Well, when I say bonus math, is in the next section, actually, we formally get these definitions. But I think we can do some really interesting things with them here in today's class. And so I'd like to start playing with these a little bit early. I think it'll really help us out moving on to the next section, 11.6. And so let me give you these definitions. They're fairly straightforward here. The sum, right, the series here of these a sub n's is called absolutely convergent if something stronger is true. And that is, if you were to sum up and make everything positive. Of course, everyone's favorite way to make everything positive is the absolute value. And so you were to make all of those terms positive, then it converges, right? So that is the condition for what's known as absolutely convergent. You can see the name wasn't very clever or anything since we have absolute values here. The second thing, conditionally convergent. Conditionally convergent is this very interesting case where the original sum converges. So, okay, so let's say the original series, that converges, and yet, if you add those absolute values, it diverges. So the absolute values kind of change things, right? It's sitting right on the edge, right? Without those absolute values, it does converge to a finite number, but if you add those absolute values in, then it's going to diverge, right? It probably goes to infinity. And so now we have more bins to place things in, and that's kind of the game that I'd like to play here, right? Now we can talk about and looking at this next example here, we'll show you the bins, right? Is something absolutely convergent? Is it conditionally convergent? Or is it divergent? So those are going to be our 3 bins, right? And for a lot of our series before today, right, they've just been positive. And so it doesn't really, right, those absolute values haven't really made a difference. But here when we're talking about alternating series, well, half the time they used to be positive, half the time they used to be negative. And now, right, those absolute values really do make a difference. And so I'd like to kind of go over a few examples with these new bins, right? Is it absolutely convergent, conditionally convergent, or divergent? And so let's work our way down, right? So the way that I'm going to do this is I'm going to first check absolutely convergent, right? Maybe it falls into this category here. And of course, the way that we check absolutely convergent is that instead of looking at the original sum or the original series, we're going to include some absolute values. And let me go ahead, I'm going to rewrite this thing here. -1 to the n times 1 over 3n minus 1. Okay, and I guess we're summing up, I'll include this, doesn't really matter, summing up from n equals 1 to infinity. And remember, a great property about the absolute values is that you're allowed to break them up across multiplication, right? So I'm going to go ahead and write this, n equals 1 to infinity, and I'm going to apply my absolute value to -1 to the n, and then I'm going to apply the absolute value to 1 over 3n minus 1. All right, so the big thing here is that, take a look, the first bit, the alternating piece, it goes back and forth between -1, +1, -1, +1, -1, +1. How much fun, right? But when you take the absolute value of either -1 or +1, right, that is always 1. And so this right here simplifies wildly, and right, it becomes so much nicer. This is just always 1. So again, let's say I'm writing maybe my next line. So when I apply the absolute value to this alternating piece, it's just 1. And now when I apply my absolute value to this other piece, right, well, this is supposed to be the solely positive piece, right? 1 over 3n minus 1, right? If I plugged in n equals 1, that would be a half. If I plugged in n equals 2, that'd be a fifth. If I plug in n equals 3, that's going to be an eighth, right? It's always positive. So what are those absolute values doing? Well, nothing, right? Absolute values don't really influence positive numbers. They only influence the negative numbers. And so this right here, right, you can just kind of get rid of those absolute values. And so our question is, right, if I'm trying to figure out, does it converge absolutely or does it absolutely converge, right? Well, does this new made up series here, the one that when I apply my absolute values, does it converge? And so now I'm looking at this right here, and I'm kind of back in earlier days, right, from chapter 11, right? I'm trying to figure out, does this series, the solely positive series, converge? And we had a lot of great tools for that, right? We had things like the integral test or geometric series test, nth term test for divergence, all that sort of stuff. And so now we have to decide, right, from that list of stuff that we know from before, right, does this converge or diverge? And certainly when I stare at this, I notice that, oh, this is kind of like 1 over n, right? I'm going to say that this is maybe like similar to, 1 over, and maybe I can leave the 3 there, 1 over 3n or 1 over n or something like this. So what I'm doing in my mind right here is that I'm making a comparison, right? I'm saying it's kind of like this, right? And then this, of course, I could tell very quickly that this diverges because of p series. So all this is what I'm thinking. Of course, I need to formalize that. And the way that we formalize it is with the limit comparison test, right? That comparison that I'm making, hey, it's like this. We formalize that with the limit comparison test. So let me go ahead and let's write out some more formal work. That's our idea here, is that I want to show that this is similar to maybe 1 over 3n. So I'm going to compare with 1 over 3n. And so, of course, the way that we do this is with the limit as n goes to infinity. And we have our a sub n's, so 1 divided by 3n minus 1, divided by our b sub n's, the thing that we're actually comparing with. Maybe let me just so I, getting in good habits for showing our work and everything, I'm going to say I'm going to compare with 1 over 3n. So, okay, then this kind of makes more sense what I'm doing here, taking this limit. Let's see, I have a bunch of fractions divided by fractions and all that sort of stuff. So let's go ahead and multiply by a reciprocal. So this one stays the same, and then I'm going to multiply by 3n divided by 1. And Maybe I could do one more line of simplification here, 3n divided by 3n minus 1. And at this point, right, I'm going to go back and I'm going to use my algebra technique here. I see that I have a polynomial on top of degree 1, a polynomial on bottom of degree 1. And so back from our algebra days, if we're taking these, talking about horizontal asymptotes and the limits as n goes to infinity, right, we know that because these polynomials have equal degree, that the limit is just going to be the ratio of the leading coefficients. So in this case, 3 over 3, which is 1. So with this, remember, we have shown that we've made some good comparison, right? That our series here, my 1 over 3n minus 1, that this is comparable with 1 over 3n. And so, okay, well, let's go ahead and make this comparison with this nicer one. And we know that they share the same fate. And so I'm going to conclude with, so since 1 over 3n diverges by p-series, sadly, we've shown that 1 over 3n minus 1 also diverges by the limit comparison test. All right, so all of that work right there is to say, no, it is not absolutely convergent. We found that when you apply that absolute value there, that makes it diverge, right? And so therefore it is not absolutely convergent. And so now we need to go into the next bucket, right? And say, okay, well, how about with conditionally convergent? So let me go ahead and I'm just going to separate my work here with just a nice little line. And we're going to check, is it conditionally convergent? So notice for conditional convergence, we've already shown half the things, right? We've shown that when you apply those absolute values that it diverges. So that work is not useless here, right? Okay, so we need to check, right? How about when you don't apply those absolute values? So when you don't apply those absolute values, again, the original series is just -1 to the n divided by 3n minus 1. And actually, I probably should have rewritten this. Let me go ahead and cheat using technology a little bit and just kind of separate the oscillating piece, right, from the positive piece. Right, and so I'm thinking, right, we're in 11.5, that I could use the alternating series test maybe, right? And so the alternating series test, we need to see, again, it's kind of a condition based on our positive piece, our b sub n's, right? Does this decrease, and is it, is the limit going to 0? So I'm going to say 1, that 1 over, actually, let me just, I'll write out the answer here, that 3n minus 1 is increasing. So the reciprocal, 1 over 3n minus 1, is decreasing. So that works out. It's decreasing. So again, this was work for decreasing. The second condition is that we need to look at the limit, right? The limit as n goes to 0, the limit as n goes to infinity of this sequence here, our b sub n's, and we hope that it's 0, and in this case it indeed is, right? Because again, that bottom piece is increasing to infinity, right? 1 divided by a very, very large number is going to be 0. And so we have the two conditions met, and so by the alternating series test, our original series, summing up our a sub n's, converges. And so remember, conditionally convergent is that the original series converges, but when you add those absolute values, it diverges. So we indeed are in this case where it's conditionally convergent. So here's a place where you see that adding those absolute values does actually possibly change things. All right, so maybe I would conclude down here with this work. I can say, so the series is conditionally convergent. All right, so there is an interesting example, right? How an introduction to these new terms, absolutely convergent and conditionally convergent. Here is another problem related to the same thing. Again, we're trying to put it now into one of 3 bins, right? absolutely convergent, conditionally convergent, or divergent. This one I've made for you, so I'd like you to spend a couple minutes, pause the video, try this one out on your own, and then we're going to talk about it together. So again, please pause the video now, work on this one, and then we'll go over it together. All right, so we can see that this one actually ends up being a little bit nicer than my first example. And I wanted to show you too that this is really all the work. Once you've done enough of these, this is all the work that's really required for showing that these absolute values just really influence the alternating piece. So that becomes 1 here, and then the bottom, right, n squared plus 3, that's already positive, so the absolute values aren't doing anything. So this is the kind of work that I would expect to see on a quiz or an exam from a student. So when we apply those absolute values, again, we're trying to check for absolute convergence. And we see this, and now we're back and we're thinking, okay, how can I solve, how can I figure out if this converges or not? And so we think back to all of our previous stuff from chapter 11, and we start thinking about the nth term test for divergence, the geometric series test, the integral test, all that sort of stuff. And certainly the easiest way to do this is going to be with the limit comparison test yet again. And so if I use the limit comparison test with 1 over n squared, again, just kind of taking the most important piece here, right, kind of getting rid of that 3, 1 over n squared, try that as a comparison. We can see that this limit does indeed equal 1, and so we've made a good comparison, right? These two are comparable, and so they share the same fate. And so, well, we take the easier one, right? 1 over n squared, we know that converges very quickly because of the p-series test. And so our more complicated series must also converge because they share that same fate, right? They're comparable, so it also converges by the limit comparison test. And since we were checking, right, is it absolutely convergent, we're just done, right? That's all we need to show. So the series is absolutely convergent. I found that it actually belongs in this first bin that I checked. How wonderful. And so that's all there is to it. But usually when I'm in class and I bring this up, it raises a kind of side question. They say, well, what about if you didn't have that absolute value? And that is a valid question. It's something that we formalize in 11.6, but for the time being, let me give you this bonus theorem. And again, we show this in 11.6. And that is if the series is absolutely convergent, right? So when you apply those absolute values, if you can show that this converges, then your work is done. Then actually we know for certain that the original series also converges. So that's a nice theorem that, again, we formally get in 11.6, and that's why you don't have to check, right, if that the original series converges or not. Because if you have the absolute value of the series converging, then that's actually a stronger condition, and it implies that you get this for free, right, that the actual series itself will also converge. So that's why you don't have any more work to show. So with that, we are all done with example 10. All right, let's go ahead and move on. I got one more page for us. Again, we're trying to put it into one of these 3 bins: absolutely convergent, conditionally convergent, or divergent. And so again, let me pause the video here. I want to give you some time to work on this one on your own. And then when you're ready, go ahead and unpause the video and I'll spoil the surprise. All right, so here is, I think, the minimum amount of work that we would need to show. You probably did a bit more than this, but let me go through my thought process with you. So again, if I'm thinking about absolutely convergent, well, we would apply an absolute value, right? And this alternating piece would be gone. And then the question is, well, how do I show that this series right here converges or diverges? And looking at this, we can see that, right, we have n in the numerator, and the natural log of essentially n, but it's the natural log of n plus 1 in the denominator. And, well, right, natural logs, they go off to infinity, but they do it quite slowly, right? N goes off to infinity a bit faster. So I actually think that this numerator is more powerful than the denominator. And so I'm concerned, right, if this sequence itself would go to 0. So I am very interested in the nth term test for divergence. And so I want to check with the nth term test for divergence, and that's this kind of work down here. And so I'm just going to take the limit as n goes to infinity. we need to apply L'Hopital's rule. So we apply L'Hopital's rule and we take the derivative of the top, that's just 1, and we take the derivative of the bottom, right? So the derivative of the natural log is 1 over, fine, do all that. We should simplify, so we have fractions over fractions, so let's multiply by the reciprocal. And as n goes to infinity, indeed we see that this goes off to infinity, right? We have infinity plus 1, still infinity, still an arbitrarily large number. And so, yes, it fails the nth term test for divergence, or that is to say, right, it diverges because of the nth term test for divergence. That's not 0, right? And okay, so we know that it is certainly not absolutely convergent. And now we have to think about conditionally convergent. And we get a scenario that's very similar to this tangent inverse thing back here, right? Where was it? All the way back here, right? Now, instead of going off to pi over 2, though, right, it went off to infinity. And when you add in that alternating piece where it starts off negative, then positive, then negative, now positive, now negative, it's going to go back and forth between positive infinity and negative infinity, right? It's going to be getting closer and closer to positive infinity and negative infinity. And the big thing here is that it's not going to converge to any one value. And so I've just kind of abused some notation here, and I've said that the overall limit, right, when I include that alternating piece, it does not exist. And so, because again, it's alternating, it's going back and forth between positive infinity and negative infinity. And so by the nth term test, kind of notice what we were trying to do is trying to figure out, does it conditionally converge because of the alternating series test? But we accidentally stumbled upon this answer here, right, that in fact, the series itself must diverge, right, because of this nth term test for divergence. So it doesn't converge to anything. It alternates back and forth, getting larger and larger and larger. So we get something like this. You know, I think that this is a wonderful time as any, right? Maybe we should just go ahead and plot what this kind of looks like in Desmos. So I'm going to go ahead and pause the video. I'm going to get Desmos up, and then let's actually take a look at what this thing really is. All right, so here I am in Desmos. I've plotted my sequence here. So I just have these. They need the variable x for whatever reason, so okay. I'm going to be plotting the points. That's what that code's for. And there is our list of items. So I'm starting off here at 4. You can see that I only have 1 dot plotted here. And I'm going to plot some dots. So I'm going to go ahead and just use this. And we can see that this is what kind of the sequence is doing. Let me go ahead and maybe zoom in on these. This kind of looks like a function here, but you can see they're actually all individual dots. And so you can see that, again, all of the even x's, right, that -1 raised to an even number, that's going to be this whole positive line here, right? And it's getting larger and larger. And then this, all of the odds, right, those are all a bunch of odd numbers, right? They're negative and they're going farther and farther away. And so I just have the first 100, but if you wanted to, right, you could play with this and say we're going to go all the way up to 1,000 or 10,000 or something like this. And you could really have a lot of fun with this. Oh, it doesn't like that many numbers apparently. All right, fine. We'll bring it back down. Where was it? So here around 3,000 apparently is its limit. And you can see that, yeah, it's just going off to infinity. There's at 3,000. So it's just trotting along there. Those are, again, all of the even values when we plug those in. And then we have all the odds down below. So that's kind of what it's looking like, right? One arc is going off towards positive infinity. One's going off to negative infinity. And so, again, by the nth term test, that's not 0. That does not exist. And so, yep, that series, when we try to add all those things together, that's going to diverge. All right, I have one more here. Again, this is kind of a difficult one. So a bit of a challenging problem here, I suppose. But again, same sort of game. Does it absolutely converge? Does it conditionally converge? Does it diverge? What's going on here? And the series here is fairly complicated, right? So I have this e to the negative n squared. And so again, let me go and I'm going to search for absolutely convergent. So maybe we're getting a little bit faster about this. And so we're going to apply those absolute values, summing up the absolute value, -1 to the n e to the negative n squared. And again, those absolute values are really only going to be taking away that alternating piece, that -1 or +1, right? That's just going to go to 1. And then let me go ahead and rewrite this, right? Whenever we have a negative exponent, that's going to be the same thing as the reciprocal, right? 1 over e to the n squared. And here we are at the challenging piece, right? And I invite you to pause the video here and try to go through your list of things and determine, does this converge or does this diverge? I'll give you some hints that this is not a geometric series, right? That squaring bit kind of ruins things. I'm not sure if I would want to integrate this if I were you. So yeah, go down the list, try to think about what to do. I'm going to let you think for a second. So pause the video, then come back and we'll talk about it together. All right. So the answer is the direct comparison test. So the limit comparison test is going to have some issues and whatnot, but with the direct comparison test, we can actually compare this with something that's considerably easier to deal with, and that is 1 over e to the n. And that's why this one's kind of clever. Again, a great in-class problem and something for us to go over together, but fairly complicated, especially for a time scenario here. And so let me show you, or at least convince you of why this works, right? So I claim that it is less than or equal to 1 over e to the n. And that's because, right, if you start to plug in some of these values, n equals 1, n equals 2, n equals 3, so on and so forth, you can kind of see what's happening here, right? So at n equals 1, we just have, well, that's the equals case, 1 over e versus 1 over e. So it's literally me just plugging in 1 everywhere I see an n. If I plug in n equals 2, well, I have to square one of them, right? 1 over e to the 2 squared, so that's going to be e to the 4th power there. And we've divided by more, right? If you literally plug that into a calculator, remember e is around like 2 or 3. It's kind of between these, right? And so you have something like 1 over 81 versus, 1 over 9 or something like this. We've divided by more. We've divided by a larger number. And as we know, when you divide by a larger number, you get a smaller quantity out. And so that's what keeps on happening here. 1 over e to the 9, right, is going to be less than 1 over e cubed because, again, we've divided by a larger number. And when you divide by that larger number, again, you get a smaller quantity. And so the trend just continues. And so I say, fine, right, that inequality holds. Who cares, right? How does this help us? Well, this thing right here is a geometric series. So 1 over e to the n, that's going to be the same thing as summing up 1 over e, all raised to the n. So this is maybe my a, and this is my r, right? And the big thing here is that r is less than 1, right? Or the absolute value of that r is less than 1. So this is going to converge by the geometric series test. All right, so let's go back over. What did we all do here? Well, we applied an absolute value, and we were trying to figure out, does this converge or not? We said, why don't we go ahead and compare it with this? And this is kind of the clever bit right here. And we showed that this bigger function converges, thanks to the geometric series test. And so if this bigger function converges, or this bigger series converges, right? What does that mean about smaller series? Is there any way that the smaller series could go to infinity if the bigger one converges to something like 50 or 13 or whatever, right? Well, no, right? There's no way that a smaller series is going to go off to infinity. So by the direct comparison test, that smaller series also converges. And because this converges, we know, and I'm going to say, and so our original series, which had this alternating piece, we know which bin this goes into, right? When we applied that absolute value, it converged. And so the answer is that this absolutely converges. And so that right there would be my final answer. All right, so that's all the work that I would show in order to say that this absolutely converges. Again, a wonderful in-class problem and something interesting for us to think about together. Not maybe the best problem ever for a timed assessment. However, I mean, you just saw this here, so I mean, maybe the next time you see it, or the so on and so forth, right? It's a little bit easier each time after this. So I don't know, maybe. For today, thank you very much for watching. Again, if you have any questions, please post them on Piazza. we're going to try to make this transition to the online class as smooth as possible. But it's going to be up to you. You're going to have to stay, motivated and dedicated to the class, and continue to watch these videos, continue to ask questions, continue to do the web work, homework, all that sort of stuff, so that way you can succeed and get a good grade in this class. So again, good luck, and I hope to see you when we return, hopefully April 20th, if not, maybe in the fall. All right, I'll see you guys out there.